Hi, I'm recording these videos as we go along, so if you have suggestions on how they could be made more helpful, feel free to email me and let me know what you would like to see. I may or may not be able to accommodate what you want, but I'd be glad to hear. This video is going to have two sections, section 2.4 about spanning trees and then section 2.5 about task scheduling. The two topics both use graphs, but other than that they don't have very much to do together. They're just being bundled together here for purposes of the course logistics. Let's first talk about spanning trees. Suppose this graph represents the buildings on a campus, maybe IWU's campus, some of them. And all of IWU's buildings are internet wired. I think they all have wireless internet, in fact. But between the buildings there is fiber optic trunk cable running, and it runs from each building back to some switching center at Information Technologies. Obviously we want all buildings to be connected to the network, but it's not necessarily the case that all buildings have to be connected to each other by internet. So by internet cable. So for example, if you're in building A and you want to talk to somebody through the internet in building D, to send an email for example, if A can talk to B and B can talk to D, then the signal can take a route like this, and there would not have to be extra cable from A to D. It would be redundant to do so, in fact. And so the goal of this problem now is going to be to make sure that all of the vertices are linked together, but to do so in the lowest cost way possible. This is going to involve constructing a tree. A tree is a special type of graph with two characteristics. First of all, it's connected, and second of all, it has no circuits. The graph on the right is such an example. It obviously is connected, and there are no circuits. You cannot travel around this graph and return to your starting vertex without retracing at least one edge. Question: how many edges are there in a tree with n vertices? Well, in this picture there are 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices, and 1, 2, 3, 4, 5, 6, 7, 8 edges. So what's the relationship between 9 and 8? Well, they differ by 1, of course. Would that be true with different sizes of graphs? If you think about it, if you had the vertices in place to begin with, then you would need one edge to connect the first two vertices. So that's one edge for two vertices. Now if you have another vertex, you're going to need one more edge, so that would be two edges for three vertices. And if you throw in another vertex, you also have to throw in another edge to connect it. So that's three edges for four vertices, four edges for five vertices, and so on. So yes, that pattern holds. In fact, if we have n vertices, we're going to need n minus 1 edges to build a tree out of them. And so in the problem and algorithm that we're about to consider, we're going to be constructing trees. And how do you know when you're finished? Well, when you have one fewer edges than you have vertices, that's sufficient to be a tree for that graph. And in particular, we're talking about spanning trees. Let's just put an example on this graph, and then we'll talk about an algorithm for finding the best spanning tree. If I throw in edges, say AB and BE and DB and BC, there's an example of a spanning tree for this graph. Notice 5 vertices, 4 edges, and if you just look at the vertices and the red edges that we've chosen, that is a tree. There are no circuits and it's connected, so that's a spanning tree for this graph. Of course, the edges have weights on them, and so we could talk about the weight of this tree or the size of this tree or cost of this tree. The 0.7 plus the 1.2 plus the 1.3 plus the 1.6 and so on. There are other trees for this graph, and some of those other ones may have lower total cost than what this tree has. So the obvious question is, how can I find the best spanning tree, the lowest cost spanning tree? Turns out that's a pretty easy problem, and I think actually you would discover this algorithm on your own even if it had not been presented to you. But Mr. Kruskal apparently was the first person to consider this type of question, and so the algorithm gets named after him. The algorithm is really simple, really intuitive. You just sort the edges in order, increasing order, and then add the lowest cost edge that you haven't used so far, as long as it doesn't complete a circuit. And then you go and pick the next edge not yet used, and if it doesn't complete a circuit, you throw it into the spanning tree. And when all vertices are reached, in other words, when a tree has actually been constructed, a spanning tree has been constructed, then you stop. Let's look at an example of this. Same graph. Here are the edges with their weights listed, and notice they've been sorted in increasing order, as we said. And now let's apply Kruskal's algorithm. Edge DE is here. It's of weight 0.5. I ask, would throwing it in create a circuit? Well, no, of course not. I haven't even added anything yet. So we'll put that in the tree. Edge AD. Would adding that create a circuit? No. So it being the next most expensive edge, I put it in. AE is 0.65. Would that create a circuit? Yes. So I don't use that one. It would be redundant to use that one. I would be using more internet cable than I need. How about AB? It's up here, the 0.7. That would not create a circuit, so yes, I throw that one in. And CD is right here. Would that create a circuit? No. So I put in the 0.75. And if I look at the red shaded edges used, that in fact is a spanning tree. Notice no circuits, but all vertices have been reached by an edge, and so this would be an example of how you could construct internet cable here. From each of the vertices, I can email or talk to any of the other vertices. As far as total cost, then, we've used an edge with weight 0.5 and 0.6 and 0.7 and 0.75. And if you add that together, I believe you get 2.55. Is that the best one? Yes. Kruskal's algorithm, in fact, is a algorithm for finding the exact solution. Remember the case for the traveling salesman problem, we had to settle for a heuristic algorithm that would find a good one, a good solution, but not necessarily the best solution. Here we are guaranteed. We have found a solution that's as good as any other, maybe better than any other. Here's another example. And by the way, as I'm presenting these examples, I'm going to work them out, but it may be to your benefit to pause the video and try to work the example yourself before you see the solution. Okay, first we're supposed to list the edges in increasing order. So ED has length 6, CF has length 7, CB has length 8, and let's see, BE has length 9, EA length 10, BA length 11, EF, length 12, BF, length 13, and finally AD, length 15. Okay, and applying Kruskal, ED of length 6. Does it complete a circuit? No. In fact, you can always use the first edge. You can't complete a circuit with just one edge, so that's an automatic. CF, length 7. That would not complete a circuit, so I'll put that into the spanning tree. Notice that Kruskal's algorithm does not work by hooking edge to edge to edge and so on. It inserts edges, and then perhaps at the last step, and only at the last step, does everything get hooked together. But you just follow the algorithm. CB of length 8, that would work. And BE has length 9, that would work. Do we have a spanning tree yet? No, we haven't gotten to vertex A. Notice that we have 6 vertices here, so we're going to need 5 edges, in fact, for a tree, and we have 4. So one more edge has to go in. The next candidate is EA of length 10, and that would not complete a circuit, and so we'll put that in there. And there are 5 edges, and there's the spanning tree. We know its cost is minimal, and that cost is the 6 plus 7 plus 8 plus 9 plus 10 is 40. Very straightforward. I hope you agree. Is there an efficient computer algorithm to find a minimal cost spanning tree? Yes, we just did it. Kruskal's algorithm. We did it, and it's very straightforward for us as humans. In fact, this is fairly straightforward to implement in a computer program. And so large, very large spanning tree problems can be done on high-speed computers. Reminder that you're supposed to be keeping track of what's quote-unquote easy and what's quote-unquote hard. We talked about Euler circuits and the Chinese postman problem. Those were easy for a computer. We talked about Hamiltonian circuits and the traveling salesman problem that went with them. That turned out to be hard for a computer. Now we've just talked about spanning trees, and that turns out to be easy for a computer. So to summarize what we've done so far, this was easy, hard, and easy. Okay. That's what I want to say about spanning trees. Before I go on to the other topic, just a comment about another place where graphs would be used in relationship to some of the topics that we are talking about. I claim that the web, the internet itself, is a graph, in fact is a directed graph. So here are vertices, and when I say directed graph, I mean that the edges actually have arrows on them, so they're like a one-directional, one-way street. How's that work? Well, the internet has 2 parts. One are websites or web pages themselves, and the other are links, how you get to a page from another page. So if you think about it, the vertices are places where information is stored. That would be represented by the numbers here. The vertices are websites or web pages, as you wish. And the edges then are the links. If this is my web page and this is yours, and I have linked to your page, if somebody's at my page, they can navigate to yours. The edges are directed or one-way directed because just because I link to your page doesn't necessarily mean that you link to my page. And search engines like Google and Yahoo and others constantly have what are called web crawlers operating. There are automatic computer programs that are simply navigating around the web, and as people add links to new sites, those web crawlers discover them and report back to Google so that they can add them to their search pages. That's how web pages are discovered. When you create a website, you don't necessarily report it to anyone until somebody links to it, or until you link to it from another page. It's not going to be discovered and cataloged on a search engine like Google. So the entire internet, worldwide internet, is an example of a directed graph, and Google has to store that information. You may know that Google makes a copy of the entire internet in storage, which they call cache. So if the actual website is not available, Google offers you the option of going to a cached or a stored version of that site. And how does Google maintain this information? Well, I don't know their exact storage algorithm, but the structure is identical to a graph situation like this. Okay, the other topic, critical path analysis leading into task scheduling. If I had written the book, actually section 2.5 would have been part of chapter 3. So this section, this topic, is going to blend into the first few sections of chapter 3. And first we're going to cover an overview of the task at hand. It's planning and scheduling. So there are lots of people available to do a very complicated task, and that task can be broken down into simpler tasks, and so now you have to decide who's going to do what. And our goal probably is going to be to get the job done as quickly as possible. If you've ever organized a project with multiple people, you have exactly that situation to do. Who's going to do what? How can we make most efficient use of the help that we have? What's an example of an industry or a group of users who would want to do something like this? Think about the airlines again. When a aircraft is expensive to purchase and to maintain. So obviously the airlines want to keep their planes in the air as much as possible. They fly and they fly, they change crews, but they keep flying. And except for maintenance time, the airline would prefer to keep its planes in the air as much as possible during the day, because that's how they're generating revenue, by carrying passengers and freight. So the airplane lands at an airport, and there are lots of things that need to happen. Passengers need to get off, and other passengers need to get on. Luggage needs to be taken off, and other luggage put on. The plane needs to be refueled. Food needs to be put on the plane, and trash taken off. Let's see, there's probably some cleaning that needs to be done, and other tasks that most of us don't know about unless you've happened to have had this particular job. All of that needs to be done very quickly, and some of it can be done in parallel. So for example, the luggage is being unloaded while we are getting off the plane. Those two things can happen at the same time. But other things can't be done at the same time. You can't have passengers getting off the plane while the new passengers are trying to get on. Let's look at a simpler situation. Not as realistic, but easier for us to analyze. Suppose you have two waiters, and they're trying to set a table for a formal dinner. And they decide that these are the tasks that they're going to need to do. And for simplicity, we're going to number those tasks T1 through T8. They also know that here's the approximate time that it's going to take one of them to do each of these individual jobs, time in minutes. And now here's an important column, prereq or prerequisite. Some of these tasks need to be done before others can be done. And we need to capture that information exactly for this to be a well-defined problem. Alright, let's analyze them one at a time. The tasks are selecting the tablecloth, putting it on the table, putting plates on the table, putting napkins on the plates, putting cups on the table, filling the cups to the brim, I say, setting the room temperature, and adjusting the lighting. Would any of those tasks have to be done before you could pick the tablecloth that you were going to use? I don't think so. And so task 1 has no prerequisites. Putting the tablecloth on the table. Well, you probably better pick the tablecloth before you decide to set it on the table. And so a prerequisite to task 2 is task 1. Putting plates on the table. If you ever set a table, you know that if you're going to have a tablecloth, you probably better put the tablecloth on the table before you put plates on it. So a prerequisite for T3 is T2, well, also T1. But let's just list T2 as the prerequisite, and then since T1 is a prerequisite for T2, it's understood that T1 is also a prerequisite. You may have seen something similar like that in course prerequisites in catalogs, college catalogs. For us, for example, you have to take Calculus 1 before you can take Calculus 2, and you have to take Calculus 2 before you take Calculus 3. So in Calc 3, we would just list the prerequisite as Calculus 2. And the Calc 1 prerequisite is understood because you had to have had that to get into Calc 2 to begin with. Okay, let's keep going. Putting napkins on the plates. Better have the plates on the table before that happens. So let's say T3 as a prerequisite for that. Putting cups on the table. Okay, we had better have the tablecloth on the table before we put cups on, but plates and cups could go on in either order. So the prerequisite for task 5 is 2, task 2. Filling the cups to the brim. By that I mean that it's no fair filling them in the kitchen and then carrying them out. We're going to fill the cups to the brim for whatever reason to play jokes on our guests. And so you probably want the cups on the table before you fill them so you don't spill. And so task 5 is going to be a prerequisite for task 6. Setting the room temperature. Could do that anytime. Adjusting the lighting, could do that anytime. So those two tasks have no prerequisites, and then here is the prerequisite chart. We're talking about graphs here, so let's take this information and translate it into a graph. Same information, perhaps just easier to read. And it looks like this. So remember we had 8 tasks, T1 through T8. They're listed here. And now our prerequisites are being given in terms of a directed graph. T1, remember, was a prerequisite for T2, and T2 was a prerequisite for both T3 and T5. And for example, T7 and T8 had no prerequisites. So that's why the graph looks as it does. We also had times required to complete these tasks, and those are put inside the vertex itself. So we'll draw these expanded vertices so we can put a number inside them. Task 1 took 8 minutes, task 2 took 6 minutes, and so on. This is called an order requirement digraph. The order requirement refers to the fact that it's discussing prerequisites, and digraph is a short word for directed graph, meaning that the edges have directions on them. What we're trying to do then is take our team of people and assign particular tasks to them. So suppose I have 2 people, for example, and I want to know what to give the first person, which task to give to the first person and which task to give to the second person. And you have to be careful, of course, because it's useless to say to the first person, oh, go and do task 6, for example. It's not ready to be done yet. There are various prerequisites that have to be done. Our overall goal is to finish this entire job consisting of these 8 tasks as quickly as possible. Let's make some assumptions on the people that are going to be working for us. And then after we finish here, we'll talk about how realistic these are. First assumption, that the individuals working for you are never going to share an individual task. So they're going to divide the overall work, but regarding task 1, task 2, task 3, those tasks are going to be done by a single person. They'll never stop working until they finish a particular task. Once the first person starts working on, say, task 4, he or she's going to keep working until it's finished before stopping. They'll never refuse to work. That would be great. And they all work at the same constant rate. So these people never get tired. They never take a break. They never speed up or slow down. They don't have bad Mondays or Good Fridays or anything like that. You say, well, that's not very realistic, right? Who works like that? And the answer is probably no person works like that, but computers do. These are very, very good characteristics, defining characteristics for how a computer works. And so this problem is also of great interest in computer science. As you probably know, the CPUs in computers, the one you're using right now probably, is a multi-core processor. Maybe it's a dual core. That means 2 cores or components to the central processing unit. Or maybe it's a quad core and has 4 cores. And so you have an overall job like doing some graphics presentation, and you're going to break that apart into individual pieces of it, and then hopefully you can assign one piece to the first core of your processor, another piece to the second core, perhaps another piece to the third, another piece to the fourth, so that these 4 cores in your processor can be working in parallel. That's why a multi-core processor can be faster than a single-core processor like we used to have. So this is primarily a computer science problem, although a organization like an airlines or other shipping company, for example, may also use these kinds of techniques to help them plan their job assignments. Okay, let's look then at a first component to what needs to happen to analyze this problem. Critical path analysis is the specific topic of the short section 2.4. There's some intuition that goes in here, and I think you would recognize it as well. If I have, for example, 2 people, two waiters to help set the table, and this is what the digraph looks like, the order requirement digraph. Of course, I can't start any of these tasks out here. They all have prerequisites that need to be completed first. I would have a choice. I could start at T1, T7, or T8. And of those, which do you think you'd want to start with first? I think it'd probably be a good idea to start somebody on T1 as quickly as possible, because you see that's holding up a lot of other things that need to be done. So it's sort of useless to do tasks 7 and 8 and get them done with, and then start somebody on task 1, because then the other members of the team have nothing to do until task 1 is completed. It's better to get the bottlenecks taken care of first. In this picture, T1 is a bottleneck, and then to a lesser extent T2 is a bottleneck, and so on. Not because they have low numbers, but because of where they appear in the order requirement digraph. It's better to get those tasks done as soon as you can. There's something called a critical path that helps you identify the bottlenecks specifically. What we'll do is start with a task that has no prerequisites and then just push it forward through the digraph to create a path that's as long as possible. Here's an example. Task 1, of course, has no prerequisites. No edges come into task 1. So T1, and then I can construct a path T2, and then a path can go to T3 and T4. What about its length? Well, here, instead of counting the number of edges, what we're going to do is add up the times of the vertices along that path. So 8 plus 6 plus 9 plus 4 is going to give us 27 for the length of that path. There are other paths. If I started at T1, went to T2, but then went on to T5 and on to T6, that's another possible choice. I started at a vertex with no prerequisites and pushed forward as long as I could go. That turns out to have length 22 for a total. And there are a couple of other paths as well. I could start at T7. It doesn't have any prerequisites. And then there's nowhere to push forward to. No edges come out of T7. So T7 with length 5 is a path in its own right. And likewise T8 with length 7 is a path in its own right. These are the 4 maximal length paths then, and the critical path is the one of longest length, so it is right here. Critical path, because 27 is larger than any of the other lengths that I found. Let's look at another example. Here's a graph with more possible paths than the one we just saw. And the question, what is the critical path length? There are a lot of paths here that would need to be listed if we were going to do the problem that way. Well, let's see if we can just apply some intuition. If I look over here, for example, of the 3 vertices on the left, 9 is the largest number. Of the vertices in the middle, 6 is the largest number, and of the vertices on the right, 8 is the largest number. So it seems like I would tend to favor using the 9 and the 6 and the 8 if I could, but I can't. I can't get from the 9 to the 6. And so now I'm probably going to have to drop back on one of these a little bit. So to drop back from 9 to 7 or from 6 to 3, the 9 to 7 would be the lesser step. So what about if we choose the 7 and the 6 and the 8? In other words, task 7, task 8, and task 6. That would be of length 13, and 8 is 21. Is there any way to get a path of length longer than 21? Each path that I pick in this example is going to have 2 edges and 3 vertices. So I could do a 6 plus 5 plus 2. No, that's not bigger than 21. 9 plus 3 plus 8 is not bigger than 21. That would be 20, in fact. 7, 3, 8, and so on. I don't think so. So it looks like the critical path here is going to be T7, T8, T6 of length 21. Why do we care? What's the significance of a critical path? Here it is. You can talk about, our goal is to find the shortest overall completion time. Find the schedule, find the way of assigning these tasks to the computers or the people to finish the overall job in the shortest way possible. Maybe we'll think of a way to allow an individual task to be done more quickly. Will that speed up the overall job time? Maybe not. If 2 people are working together on jobs that have some relationship and one person speeds up, the other person may or may not be able to also compensate so that the overall job can be completed in faster time. In other words, if you're working with somebody else and you decide to work faster, the overall job may or may not get done any faster depending on what the other person does and what your relationship and their relationship is in terms of their individual work and how those tasks fit together. So completing the overall completion time will be reduced only if that task is on the critical path. The critical path, it turns out, controls the overall completion time. It doesn't flat out give the overall completion time, but it controls it. If you're going to work on reducing task times of individual tasks, you better focus on those tasks that are on the critical path. We'll come back to this topic in Chapter 3 in much more detail. Thanks.